Last time we started to talk about hypothesis testing, which is the reason for much of social research. It may be the reason for all social research. And certainly is at the heart of communication research. We started we did two things, I think. We looked at some general issues associated with hypothesis testing. First of all, we looked at two components of that. One, which we can sort of push aside for the moment, is the issue of type 1 and type 2 errors. And we found, I think just as in a court of law, that social scientists, like juries, can make mistakes. And there are two types of mistake in social research. A type 1 error where you reject a false null hypothesis, reject a true null hypothesis, and a type 2 error in which you fail to reject a false null hypothesis. Let me ask, are there any questions about type 1 and type 2 errors? The second thing we looked at then was the issue of alpha. The likelihood or willingness to commit a type 1 error. And we observed two things. First of all, that the level of alpha is selected by the researcher. And second, that by convention, alpha is set equal to 0.05 or 0.01. In some sorts of research, such as medical research, alpha is often set even lower, 0.001 and so forth, simply because of the nature of the consequences associated with committing a type 1 error in medical research. A type 1 error in medical research is to release onto the market, believing it is effective, a new drug that is simply ineffective, or a new dose size for that drug which is simply which in reality is ineffective. But in social sciences, alpha by convention is set at either 0.05 or 0.01. We then work through an example of hypothesis testing in its simplest form. We compared a sample to a population. We compared X bar to mu, and the issue was, is X bar significantly different from mu? And I tried to, last time, indicate to you how that is associated with, tied to alpha. And second, that in order to reject the null hypothesis, the single sample mean must be significantly different to the population mean. And by significantly different, what we mean is that the probability of committing a type 1 error is less than the researcher's willingness to commit a type 1 error. That involves something that we didn't talk about but is discussed in the text. It involves a comparison of P with alpha. No matter what data analysis you run, at the end of that analysis, you will be given a p-value. And researchers report that p-value in the articles that you have read or will read or are reading. If the researcher has, for example, established alpha at 0.05, and if the p-value is 0.03, then the researcher would reject the null hypothesis. Because the researcher is being told that if she or he rejects the null hypothesis, there is a 3 in 100 chance that she or he will commit a type 1 error. And if the researcher has established alpha equal to 0.05, the researcher has said that she or he is willing to take a 5 in 100 chance of committing a type 1 error. When P is less than alpha, the researcher will reject the null hypothesis. If we had a second researcher who, rather than set alpha equal to 0.05, had set alpha equal to 0.01, this researcher, the second researcher, is willing to take only a 1 in 100 chance of committing a type 1 error and is being told that if she or he rejects the null hypothesis, there is a 3 in 100 chance of committing a type 1 error. That researcher then would fail to reject the null hypothesis. So when P is less than alpha, the researcher rejects the null hypothesis, and when P is greater than alpha, the researcher fails to reject the null hypothesis. Let me just introduce here a cautionary word that is really parenthetical to the course. You do not have to, as a consumer of the research, accept the researcher's decision. And in specific, you do not have to accept the researcher's level of alpha. Because some researchers will set, for example, alpha equal to 0.10. If the associated p-value, that is, the p-value associated with the analysis, is 0.08, this researcher who has set alpha equal to 0.10 will, of course, reject the null hypothesis. You should understand that this is an unacceptably high level of alpha. And you as a consumer should fail to reject the null hypothesis because in your head you should establish alpha at some lower and more conventional level. Are there any questions about alpha or p-values? There is one other thing that we need to look at before we go through some examples of hypothesis testing, and that is the issue of whether the test should be one or two-tailed. Oh, goodness gracious. I lost that, didn't I? This is a sampling distribution. And we've talked so far about a sampling distribution of sample means. At the center of that distribution is the population mean mu. We took a single sample mean in the context of hypothesis testing, and we standardized that single sample mean and we placed it in this sampling distribution of sample means, and that allowed us to make our decision. Let us assume, first of all, that alpha equals 0.05. Let's assume as well that the researcher argues that X bar will differ from mu. This researcher must conduct a two-tailed test, because arguing simple difference is to actually posit two possibilities. One possibility is that X bar will be greater than mu, and the other possibility is that X bar will be less than mu. So if a researcher simply hypothesizes difference between two scores, then the researcher must conduct a two-tailed test. If alpha is equal to 0.05. That means that the researcher must deploy half of that error, 0.025, at the negative end of the distribution, testing for negative difference, and half of alpha, 0.025, at the positive end of the distribution to test for positive difference. Does that make sense? Yes.
So if it shows equality, it's going to be a one-tailed test. If it shows great,
no. Let's not get ahead of the tour. All you need to understand at this point is that if the researcher hypothesizes difference, because difference can occur in two directions, the researcher has to test for both positive difference and for negative difference. And the practical implication of that is that whatever alpha the researcher has established must be deployed at both ends of the distribution. And the typical way of doing that, the standard way of doing that, is to deploy half of alpha at one end of the distribution and half at the other. And if you go to table A, looking for an area beyond Z of 0.025, you'll find that the magic Z-score is plus 1.96 and minus 1.96. That is, in order to reject the null hypothesis in this instance, the observed value of Z must be either less than minus 1.96, that's in this shaded region here, or greater than plus 1.96. That's in this shaded region at the positive end of the distribution. If the observed Z-score falls between those two boundaries, that is, in this area, the researcher would fail to reject the null hypothesis. Yes.
Which number did you look on in the table A to get the 0.196?
1.96. You'd be looking for a Z-score that's associated with an area beyond Z of 0.025.
So when you have a two-tailed test, you can just do alpha divided by 2, and that's how you get your 2.
That's right.
Okay.
So if alpha were 0.01, you would deploy half of alpha, 0.005, at this end of the distribution and half at the positive end of the distribution. And you would go to table A to find an area beyond Z of 0.005, and that magic marker would be plus and minus 2.58. Is that right? He said confidently and then not so confidently. And it would be 2.58. There are two pieces of information that you need in order to conduct hypothesis testing. One is the level of alpha, and that is under the control of the researcher. The researcher selects the level of alpha. And the other is to determine whether the test should be one or two-tailed. And if the researcher simply hypothesizes difference between two scores, two or more scores, the test must be two-tailed. If the researcher predicts not simply difference, but difference in a specific direction, for example, X bar will be greater than mu, then all 0.05 of the error of alpha can be deployed at this end of the distribution. If the researcher hypothesizes not simply difference but negative difference, that is difference in a particular direction, then all of the alpha rate can be placed in this case at the negative end of the distribution. Let's very quickly, let's start going through some examples that are more complex than comparing a sample mean to a population mean. Let's assume that a researcher predicts that the marital satisfaction of couples or people with children will differ from the marital satisfaction of couples without children. What is the research hypothesis here? We have X bar 1, because what the researcher is going to do is, rather than compare a sample mean to a population mean, the researcher is going to collect two samples. One sample comprised of people with children and one of people with no children. And the researcher is going to use some scale to measure their marital satisfaction, and then generate the means and standard deviations of those two sets of scores and compare one set to the other set. We argued moments ago that in order to test hypotheses, you need to know two pieces of information. One of those was whether the test should be one-tailed or two-tailed. If the researcher predicts that the marital satisfaction of persons with children will differ from the marital satisfaction of persons without children, should the test be one or two-tailed? They answer in unison that the test should be two-tailed. Would you agree it should be two-tailed? You concluded that it should be two-tailed because the relationship posited by the researcher is that X bar 1 will differ from X bar 2. That the marital satisfaction of persons with children will differ from the marital satisfaction of persons with no children. A simple hypothesis of difference. You should note then that the null hypothesis, which is the hypothesis actually being tested, is that X bar 1 will equal X bar 2. More specifically, that X bar 1 will not differ significantly from X bar 2. Let me stop at this point and ask if there are any questions.
Why is it they will equal each other?
Because the null hypothesis in general is a statement of no difference. Just as in a court of law, the null hypothesis is that the defendant did not commit the crime. And we could reconfigure that to say that the null hypothesis is that the defendant's presence at the crime scene made no difference to the outcome that was observed. If you, as we will see, if you hypothesize not simply difference but difference in a particular direction, then the null hypothesis changes. If you hypothesize positive difference between X bar 1 and X bar 2, then the null hypothesis is that X bar 1 will be equal to or less than X bar 2. The null hypothesis is all that the research hypothesis isn't.
So you could just say it's the opposite of what hypothesis is going to be?
Yeah, it's the converse of the research hypothesis. Are there any other questions? We're going to go through this about 4 million times, so if you don't get it right now, I wouldn't worry. The second piece of information that we needed was to determine a level of alpha. Let us presume that alpha is 0.05. Yes. If you are conducting a two-tailed test and alpha is equal to 0.05, would you agree that if we go back to our sampling distribution, that half of alpha must be deployed at the negative end of the distribution and half at the positive end of the distribution? Yes? So you're looking in Table A for an area beyond Z of 0.025 or 2.5%. And you will find that that coincides with a Z-score of 1.96. So that given these two pieces of information, we can identify the critical value of Z. And the critical value of Z is plus and minus 1.96. Would you agree? Because this boundary marker is 1.96 standard deviations above the center of the distribution, and this boundary marker is 1.96 standard deviations below the center of the distribution. So the critical value of Z is plus and minus 1.96. That means that in order to reject the null hypothesis, the observed value of Z must be in either this shaded region or in this shaded region. In order to reject the null hypothesis, the observed value of Z must be in this shaded region or in this shaded region. Oui ou non? Oui? Oui. There are a number of sampling distributions. We have talked only about a sampling distribution of sample means. But we could talk about a sampling distribution of sample mean differences. That is, x bar 1 minus x bar 2. If we reached into this population an infinite number of times, selected out samples of the same size with sample size large, that is greater than 100, and computed the difference between x bar 1 and x bar 2, we would discover that the resulting distribution of those sample, the differences between those sample means was normal. It would have a mean of 0, and it would have a standard deviation of the square root of S1 squared over N1 minus 1 plus S2 squared divided by n2 minus 1. This is simply the nature of a sampling distribution of sample mean differences. It has a mean of 0. That is, there is no difference between x bar 1 and x bar 2. And it has a standard deviation of S1 squared, that is, the standard deviation or the variance of group 1 divided by the number of people in group 1 minus 1, plus the variance of group 2 divided by the number of people in group 2 minus 1. Yeah.
Can you write that formula a little bigger?
A little bigger?
Yeah, it's hard.
This one?
Yeah, the one you just wrote.
A little bigger. S1 squared, that's not a good squared. You're going to tell me my handwriting's it's being left-handed with this, a machine that wants me to be right-handed. It's the variance of group 1, that is S1 squared, divided by N1, the number of people in that group, minus 1, plus the variance of group 2, that is S2 squared, divided by the number of people in that group, minus 1. Are we good to go? If you want it bigger, it's the square root of S1 squared. Sounds like so we're good to go. Let's get rid of this stuff. Let's assume that the researcher has two samples. Sample 1 is a sample of where, that is N1, a sample of 108 persons who have no children. And sample 2 is a sample of 102 people who have children. Let's assume further that the mean of the group with no children, this is a group with no children, this is a group with children. Let's assume that the mean level of marital satisfaction for the group with children, with no children rather, is 7.42. And that the standard deviation of those 108 scores is 3.16. Let's assume that the mean marital satisfaction expressed by the group with children is 6.72. And that the standard deviation of those scores is 3.35. Are there any questions to this point? You've got two samples. They're both large samples. One comprised of 108 people who have no children, 1 of 102 people who have children. The researcher has administered some measure of marital satisfaction. The mean level of marital satisfaction expressed by people with no children is 7.42, and the standard deviation of those scores is 3.16. The mean level of marital satisfaction expressed by people with children is 6.72, and the standard deviation of those scores is 3.35. What do you think we do with this mess? Plug it in, plug it in, plug it in. We plug it in where? What formula? For a z-score. We standardize this stuff, and then we fit it into the sampling distribution of sample mean differences. I'll go with that. Agreed? That's where we started. That's where we started. Would it surprise you if the formula in this instance for z, the numerator is x bar 1 minus x bar 2, and the denominator is the standard deviation of the sampling distribution of sample mean differences, which I think we said was S1 squared divided by N1 minus 1 plus S2 squared divided by N2 minus 1. Are we good to go? I'm pedaling along here. You've got to pedal with me. You don't have to get in front of me, but you've got to keep up. Is there anybody who feels like they've been cut adrift? Because I can slow down, I can circle back. Okay. We go on. So in this instance, would you agree z equals, and we can simply now plug it in. X bar 1 is 7.42. X bar 2 is 6.72 divided by the square root of S1 is 3.16, but we need to square that, divided by 108 N1 minus 1, which is 107, plus 3.35, which is S2 squared, divided by N2 minus 1. N2 is 102, so N2 minus 1 is 101. Yeah? I have no idea what this is, but we'll work it out. 7.42 minus 6.72, would you agree, is 0.7. Divided by, and I'm going to do this in front of you with my 408-year-old calculator, 3.16 squared divided by 107 equals whatever it equals, 0.0933 and something else. plus 3.35 squared divided by 101. And that equals 0.111, and together they equal, it equals 0.204. So it's a square root of 0.204. Okay? And the square root of 0.204 is 0.452. So that the observed z-score is 0.07 divided by 0.452, which is 1.548 plus 1.548. Okay, lads and lasses. Now you've got to get in front of me. I've done all the hard work for you. I've done, the calculations, the whole bit. At this point, how many of you would reject the null hypothesis? How many of you would conclude that people without children are significantly more satisfied with their marriage than people with children? How many of you would fail to reject the null hypothesis and conclude that there is no difference between the marital satisfaction of people with children and people without children? How many of you simply don't really have an answer? How many, I'll rephrase that. How many of you simply don't have an answer? Let me say the same thing in another way. How many of you simply don't have an answer? Let me put it this way, and I'm not going to say it again. I'm not going to say how many of you simply don't have an answer again. That would be redundant. Those people who concluded that you would fail to reject the null hypothesis are correct. Is there anybody who does not understand the logic that leads to the conclusion that you would fail to reject the null hypothesis? Three, four. I ain't going to go through it again just for four people. So how many of you don't understand the logic that leads to the correct conclusion that you would fail to reject the null hypothesis? More than four. I would have gone through it for the four. I'd have gone through it for the one to start with. Part of my rationale for pushing this issue is you don't have to be afraid in here to say, I don't understand, I don't get it. It's better that you don't get it here and admit to me that you don't get it and I can go through it again than you get on and get to an exam and don't get it there, and I'm no help. So if you don't get it, just stick up your hand and indicate that you don't get it. This is slippery stuff. In the Tour de Research Methods, we're now going up something akin to Alpe d'Huez. The critical value of Z is plus and minus 1.96. Let me get rid of some of this stuff here. This is the observed value of Z. We said at the outset, what we appealed to was a sampling distribution of sample mean differences, which we agreed was normal. Because alpha is 0.05 and we're conducting a two-tailed test, we agreed that the critical values of Z were plus and minus 1.96. That is, we agreed that in order to reject the null hypothesis, the observed value of Z would have to be in either this region, that is less than 1.96, or in this region, that is greater than plus 1.96. The observed value of Z is 1.548. It's somewhere in here. We agreed that if an observed Z-score fell in that range, we would fail to reject the null hypothesis. We would reject the null hypothesis only if the observed Z-score fell in one or other of these two shaded extreme regions. Yes.
What if it lies right on the line, like it's either 1.96 exactly or negative 1.96 exactly?
You're asking a question that's asked every semester, and I say that because you've got a lot of compatriots to whom that occurs. If the observed value of Z, or more generally the test statistic, falls right on this line or right on this line, P, the probability of committing a type 1 error, equals 0.05. Alpha you've established to be 0.05. The answer to your question is some researchers would fail to reject the null hypothesis, and some researchers would reject the null hypothesis. In reality, the likelihood of that happening is essentially zero, because you understand that these observed values of Z can go on forever. There are an infinite number of values of Z. I arbitrarily cut this value, observed value of Z, off at 3 decimal places, but there were additional decimal places. So the likelihood that the observed value of Z will precisely equal the critical value of Z is essentially zero, and it is not a situation you will encounter on an exam. But if you're the one researcher in a million to whom that happens, you flip a coin. Or you go, it depends whether it's not a matter of flipping a coin. It depends whether you're a relatively conservative researcher, you don't want to make a type 1 error, or you're a relatively liberal researcher who's more, and I use conservative and liberal in statistical sense here, who is more willing to commit a type 1 error. It's drawing a line in the sand and saying, I don't go beyond that line, and your question is, what if you land on that line? And at that point, it comes down to personal choice. I will say again that you, as consumers of research, don't have to go along with the researcher's decision, whatever it is. You can set your own level of alpha. You can make your own decisions at various points during this process. And another point at which you could, besides the level of alpha, at which you could make your own decision, would be this hypothetical circumstance in which the critical value of Z precisely equals the observed value of Z. That is, the probability of committing a type 1 error precisely matches the willingness to commit a type 1 error. Are there any other questions about this example? In this example, you would conclude that the marital satisfaction of persons with children does not differ significantly from the marital satisfaction of persons without children. You would fail to reject the null hypothesis. Yes? Let's go to a second example. Again, using marital satisfaction as the outcome or dependent variable. Let's assume that a researcher predicts that persons' marital satisfaction decreases significantly upon the birth of the first child. Let's not go any further. Given that statement, that persons' marital satisfaction decreases significantly upon the birth of the first child, and let's assume X, the first sample, is a sample of persons with no children. This is group 1. And group 2 is a group of persons who have one child. What is the relationship, predicted relationship between X bar 1 and X bar 2? Let me read it again. Persons' marital satisfaction decreases significantly upon the birth of the first child. Isn't the hypothesis that people with no children will be more maritally satisfied than people with children? That is, the research hypothesis is that X bar 1 will be greater than X bar 2. So that the null hypothesis is that X bar 1 will be less than or equal to X bar 2. What level of alpha would you like? Well, if you've got no preference, I'm going to say, let's set alpha equal to 0.01. We then have the critical value of Z. And would you agree we can determine the critical value of Z given these two pieces of information? Given that we know we're conducting a one-tailed test and alpha is equal to 0.01. Yes? Let's assume that the researcher again samples 108 people with no children, discovers that their mean marital satisfaction is 7.42, and that the standard deviation of those scores is again 3.16. Let's assume again that the researcher samples 102 people who have one child, that the mean level of satisfaction amongst those 102 people is 6.72, and that the standard deviation of those scores is 3.35. Your mission, should you decide to accept it, is to evaluate, test that hypothesis by next time. What I want you to do is go through this process by yourself. On Tuesday, when we next meet, we'll go through it in class, and we will hope that everybody has got locked in and reaches the correct conclusion. Are there any questions?
When you write H1, when it's X bar 1 is greater than X bar 2, is that what does that represent? And
that's the research hypothesis. That's what the researcher believes.
Okay, and then when X bar 1 is less than or equal to X bar 2, that's the null?
That's the null hypothesis in this case.
Because it's a one-tailed test, we're not going to have to split the alpha to both ends of the...
I have no idea. I'm sorry, Senator. I have no recollection of that meeting. That's something you'll have to decide. Was there a question at the back? Oh, yeah, we are. It's only Tuesday today, isn't it? By Thursday, you should have the answer. Are there any other questions? We're done.